on behalf of Ken and everyone here, we'd like to welcome Patrick. Patrick is obviously well known to all of you, a friend and a colleague to all of us here. So he needs no introduction, but let's just say he is initiating the pre-VVSS meeting here, inaugural talk on position effects from frames of reference. Patrick, thank you very much for agreeing to give a talk to all of us, and thanks to everybody for being here.
Okay, am I on? Yeah, okay. Okay, Christina, you'll have to keep an eye on the chat.
I can absolutely do that.
Okay. Okay, so now you have the first slide, I hope, of the talk. And we're going to start two parts. The first part is like motion-induced position shifts, and many of you know about this, so I'll try and maybe go a little bit fast. There's kind of single drift things. These are our favorite, I'm assuming you're seeing my cursor here, our favorite flash lag, flash drag, flash grab, all of these things, and then the double drift, a little bit different. And these produce very strong effects, and you'll see some of them. And interestingly, for these simple motion-induced position shifts, we have some idea about the anatomy and the mechanisms. And then the second part, of course, what you're here for, is our Stuart and my new, and Mark, sorry, Stuart, mine, Mark, new outing into frame-induced position shifts. And these are a close relative of induced motion. So any of you who have done induced motion, and that's some like Ken and Stuart and others, know a lot of this literature. So I'll mention some of it, but not much. And what we find is we can make, rather than effects of a frame on a moving stimulus, we can find the effects of a frame on position are really quite large and surprisingly large. And that's why we're interested in this. But at the moment, we have no clue about the anatomy or the mechanism. So you'll have to, come up with some wild ideas and help us out here. Okay, so now starting with the motion-induced position shifts, the single drift, like flash grab and so on. Here's 4 examples. Now here you should have your movies open and stepping through your movies, although they're arranged a bit different. So motion drag is the Ramachan and Anstis, of course, and Devoloi and Devoloi. This one here is the Devoloi, where the top and the bottom patches seem to drift towards each other or away from each other. And you notice the position offset's about 1/4 of the aperture size. Some of you are familiar with this. Other one is a bit older, so Stuart knows this one, the Froelich effect. Here you should be focusing on your movie on one of the red triangles. And you'll notice that as the motion begins, you really only notice the edge a little bit away from the start position. It did start actually be right beside the red triangle, but you might not see that because it's delayed in some way. And that's the Froelich effect. The flash lag from Nijiwan, you're familiar with that. The moving edge goes by the flashed pointer, and it seems that by the time the flash has turned off, the edge has gone far away. And that's not quite fair because you have to kind of detect the flash and then go find the motion. So along came David in 2000 and discovered this effect, the flash drag, where the moving edge reverses just as the flash happens. And you have to look in the middle now, the middle fixation point, and try and judge the relative position of the 2 flashes, the 2 red flashes on the left and the right. And I think as David reported, you'll find the flash on the left above the flash on the right. So that was the flash drag effect. And that wasn't what David was looking for, but it's what he found. It's quite cool. And nothing much, well, a lot of things happened about the flash lag in the years that followed. But then all of a sudden in 2008, Stuart came to visit in my Paris apartment, and he brought a version of David's effect, but with, instead of having the flash beside the motion, the flash was on the motion. And so this one on your movie, probably better than on the screen here, shows that when you do that, the flash is transported a huge amount away from its retinal position, about 10 times further than what it did if the flash were beside the motion. So giving us more room for testing and theorizing. And more recently, Stuart and I also found this one, which is quite similar. Again, on your movie, you should advance to the next slide and see this one in full glory. I hope the movies are working for you all. Or perhaps the screen version is not too jerky and you don't need the movie. Anyways, the red and the blue squares are identical in location and size and width and line width. But it looks like the blue one is about twice the size of the red one. So again, something about motion pulling, motion extrapolating location. So it extrapolates according to Nijiwan in his original thinking about this. Motion helps extrapolate the target to where it will be, accounting for neural delays. And there's a lot of controversy about that, but it is a useful idea, especially if you're thinking about eye movements. And of course here it's really well established that when you're making an eye movement to a moving target, your eyes land on it. Even though the programming had to be over at the time you execute the eye movement. And so you have to compensate for the delay and the motion and to land on it accurately, which you do. And this has been worked out in the physiology where Casanello, that's Carlos, found with Ferreira, found about 1/3 of the cells in the frontal eye fields code for the landing location of the saccade. Not its current retinal location, but its future position, which is where the saccade will land. In other words, the extrapolation is there explicitly in frontal eye fields. And similarly, Mohosinian and Raj Gandhi found the same thing in the superior colliculus. So the three saccade areas, which you probably know, the frontal eye fields, the parietal, and the superior colliculus, have these nice retinotopic maps. Not really retinotopic because there's some coming updating, and moving targets are moved ahead, extrapolated ahead. And it's not only in these saccade centers that, John Reynolds, who's kind of pursing his lips there, along with Kirsty Sundberg and Maz Fala, did a nice study in V4, where they also found extrapolation in cell response. They used Rick Kai's demonstration, which you see here. If you move ahead in your movies on the website there, and make it work, you probably see, if you're looking in the center, you probably see the red flashes are offset with the top red one to the right, and the bottom red one to the left, whereas the blue ones on the way back, if they show up, on mine they're not, oh, there they are sometimes. The blue ones are offset the opposite direction. In other words, they get extrapolated ahead along their path of motion. And what Christy and John and Naz did was they placed that stimulus inside passing over a receptor field, shown by that green path here, green box here. That's where the receptor field will be here, and recorded from the cell. These cells are not motion selective. They are, some of them are color selective, and you notice that the bars that's flashed are color, and so really in most cases what they were getting was a response to the color. So you see here, receptor field is that box, and the path is these different positions, and then there's a flash. At some point there's a flash, and the flash can be before or inside the receptor field. And what they found was the response, if you look here, the blue one is when the flash was in front of the receptor field and it's going this way. That's this part. Here it's in the receptor field, here it's out the receptor field. The response to the blue flash preceded the receptor field, was highest, in fact, just as you got to the edge of the receptor field, and coming back, remember these are not motion selective cells, coming back, the red curve, again, there's an offset favoring a response before you even get to the receptor field. Now this difference corresponded quite well to the perceptual offset seen by human observers, although they didn't test that in the monkeys. So there is some evidence for response as well in V4. Now, question, of course, we know that there's this correction in saccade areas and V4. Is there a similar one for perception? Is it come from the same source? We know there is an offset for perception, and perhaps a perception undergoes an equal extrapolation just to keep calibrated with the action. So just to keep in touch, right? I mean, that's the purpose of perception. which has, you know, something to do with like predicting the present. Okay, well, if you thought about that, and if you think that the saccade system has something to do with it, you would think, of course, people who have slow saccades ought to have a different perceptual effect than people who have fast saccades, because if the perception is just trying to keep the perceived location aligned with the action, the saccade, then the slower saccade should have an effect. And I think by now you figured out that, okay, people with slower saccade should have a larger perceptual effect, because there's more time, more delay that they have to overcome, and more they have to compensate for. They have to predict further ahead in the future. And that's what Ellen van Heusden, along with Henze Hoogendoorn, and the rest of us, found using, I didn't give you a movie for this because it's not too important. They asked people to judge the perceptual offset of the flash on the moving background and compare it to the saccades. Now, we already know from Anna Kosovicheva, along with David Whitney, and Schaefer and Moore, and Der Sperati, and Zimmerman, Moore, and Burr, that people, when you have a flash grab or the motion drag, the de Valois effect, that the saccades do agree with the illusion. You get the same amount of saccade shift as you get an illusory shift. Here, our question is, for people who have longer saccade latencies, do they also have larger perceptual shifts? And that's what L found. That's this curve here across the 8 subjects. So yes, there is some evidence for a link between saccade planning and the perceptual extrapolation, perceptual shift. So where does this happen? Well, there's 2 papers on the flash grab in bold in fMRI, one by Peter Kohler at Dartmouth and one by Gu in Beijing, along with Sheng He. And they both have the same result, that the activity in area V1 shows a shift. And that's interesting, but actually we believe, and these articles support the idea that it comes not from a shift that occurs in early visual cortex, but from attention. Attention has this perceptual shift much later on and projects back to early cortex, saying, this is where I think the stimulus is going to be. And that's the activity that is being picked up here. So it shifts most, interestingly, Gu and Al did this in a 7T magnet, and they were able to differentiate the different layers, top, middle, bottom, and where the upper layers get most of the downward projections. And what they found, so they did the same disk background offset. Here's their V1, so they're plotted in polar coordinates to the activity, and they match orientations to the activity patterns, and find that there is a shift in V1. When they do it in the 7T magnet, they found the shift that they measure in this manner is largest on the top layers, saying that it probably is downward projections. It's probably an attentional shift, whereas the deep layers have very little shift. Okay, now we have other evidence that early activity doesn't shift. This also is from Anna Kosovicheva in a very clever experiment on flash grab. Now we know the fMRI activation shifts, but the neural activity in V1 is still strongly bottom up. And here's her evidence. First of all, she had a rotating background that sets this thing out here. If I shake a little bit, it gets bigger. So over here, this rotates back and forth. And every time it reverses, there's a little tiny Gabor. I think you can see that right there. Be nice if I could blow that up. But anyway, a little tiny Gabor at the top and the bottom. And the Gabor is tilted. This goes on for a while. So flash, 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 lots of adaptation of that tilt. And then there's a test. And the test, of course, is either vertical, and you have to say if it's tilted left or right, looking for a orientation after effect. And Anna, along with Dave Whitney and everybody else, tested 3 locations. One, the physical location, and one was this one over here was the perceived location. So it's matched for every subject to where they saw the actual Gabor appearing. And then one on the other side, just for good measure. And this red line is kind of hypothetical result. What would happen without any of these manipulations of location? You would have the highest highest after effect at the retinal location. And of course, it drops off gradually to the left and the right of the test position, of the matched position. Now, if area V1 had an actual shift of the activity there, and so the actual cells in V1 are now responding to a tilted grating over there at the perceived location, at the perceived location, then this whole pattern should shift to the right. Should do that. That would make sense. That would say, okay, the activity now, the activity is now at the perceived location, and it should drop off to the left and the right. But in fact, what Anna found was not that. She found this. So there was a certain bias, a little amount of bias to the perceived location, a little more after effect here, as if there was a bit of a shift here, but the main effect was still retinal. And that's the point. Tilt after effect still strongest at the physical location. Therefore, there really isn't any shift of activity in V1. And the fMRI results are telling us not that the bottom-up activity got shifted, but that the top-down, the attentional feedback is there. So conclusions: perception, attention, and saccades all agree for this simple motion extrapolation. So they're all working together as they should. And they all predict a forward shift. You didn't even talk about this much. About 100 milliseconds, the shifts are all about equal to 100 milliseconds of travel of whatever motion was involved. And this position shift scales with speed. And it could be that the saccade system is the source of this location. We'll probably throw that out in a while, but let's say that for the moment. But what does say that if we do think the saccade system is involved, that studies testing models of neural delay and extrapolation, of which there have been many, but they actually need not to be run on the like flash lag or flash drag on itself, but verified in conditions with saccade, if you really want to check this out. Okay, but there's another point about attention here. Attention, we're saying it sends downward activity to the expected perceived location in V1. And that's a problem. So really attention is like everywhere. It's doing lots of good stuff, of course, telling every part of the visual system where the perceived location should be, so that those cells could get a boost. But that means you can't really find where the perceived location first emerges, because that perceived location is then broadcast back everywhere else. So that's a problem. But it wasn't a problem in one study by Fisher, Spotswood, and Whitney, so we're going to get back to that at some point. There's Fisher and Spotswood and Whitney say that they didn't find any shift in V1, and we'll see about that. Okay, that's the first part of the MIPS. The second part, of course, is double drift.
Professor Patrick, there were two questions, I believe, in the chat from this section. One was, do you have thoughts about where in the neural processing the color signal advance can take place? And this is from Christopher Tyler, and he says it cannot be at the receptive field per se because it has not reached it yet. So that was one from a couple slides back, and the other one was from Jeff Mulligan. With rotating stimuli, are torsional eye movements a concern? So if you have any thoughts on those.
Had two thoughts. On the first one, the response to the color from the moving bar in Christy Sundberg and John Reynolds' experiment, it does seem to have some advanced activity, and that can only be from feed forward lateral connections, and that's something they consider in their article. So yeah, it is responding outside its classical receptive field, and that means there's some kind of advanced warning. Hey, I've got something moving towards you. Wake up. That's my interpretation of what they said, but you really have to go read their paper.
Okay.
And the second question was about rotary things. And this was something that David Whitney dealt with a long time ago by having two rotating discs, which we also did in the first movie you saw. They're two counter-rotating discs, and so it can't be cyclotorsion because you can't move unless you're looking at both eyes separately, both discs, one with each eye, and each eye was rotating separately in opposite directions. So we think that's pretty unlikely. Okay, so here's the double drift. And what we found here, what Matteo Lisi found here, is it affects perception but not gaze. And sideways shift, it's a sideways shift. The stimulus is moving one way, but the percept slips away more and more, increasingly far, because of the internal motion of the Gabor. And this, unusually for all illusions, accumulates over a second or two. That's very, very long time constant. So it's not like the flash lag and the other extrapolations, which could have been functional. This is really an unleashed, over correction, uncalibrated response, perhaps because it's so rare in the real world. Okay, so Suzanne, bless you. So perception shifts, but eye movements and attention do not. We'll look at that later. The intention is a conjecture, but pretty, well, we'll find out. So locations from the eye movement system, therefore, cannot be the final stage of location code. Perhaps the saccade system makes a contribution, but it's not the final representation, because here we get something that dissociates perception and eye movements. And here's the data for the eye movements. What Matteo did was he presented a stimulus that appeared to move to the subjects up and down vertically, and then asked subjects just to saccade to it. And over here is the control. There's no internal motion, no illusion. Here's the physical path, the gray bar, the little red spots are the landing spots of the saccades triggered at different moments during the trajectory of the Gabor up and down. And they all fall pretty parallel. There's of course an undershoot. The fixation point was over here. There's an undershoot as there is for all saccades. On the double drift where there is an illusion, same physical path, but the perceived path is vertical now, and the saccades land up in the same place. Like there's zero difference between the control and double drift. So the illusion goes down to 0% at that point. So unaffected by the illusion. Now that conclusion that the saccades are unaffected by illusion was just challenged by Nakayama, a different Nakayama, and Holcomb, in which they said that attention resets the illusion, and they showed clearly that it does. So what this little diagram here shows is two different paths. Here's the gray bar is the physical path here in one case, and here's another one on the other case. The tracings are tracings that the subjects drew after each trial. Subjects drew what they saw. Now you see right here at the beginning that the tracing goes down. So that's the illusion that it's moved away here. But then right in the middle here, they make a flash. There's just a full screen flash, okay? And that resets the illusion back to its physical path, and then it starts again. And we've seen that, and perhaps you saw that when you were looking at our movie. But their claim there is that saccades themselves reset the illusion. And so the difference between the saccade and the perception may not be there, according to them, that saccades are not immune to illusion. Well, we've been studying that. That's Saray Liu again, who just got her PhD, Dr. Liu. And she did a study with, you had to make a saccades, and then there was a drifting Gabors in the middle of the field. And just as at the same moment you made the saccade, she offset the Gabor's path one way or the other, and you have to say, oh, are they continuous or not? So she's going to be able to tell whether the saccade has created a shift in the parent path. And it did. It did for about 50%. No illusion. Here you go. This thing is where you say aligned or not. And you align here, whereas 0 would be there was no shift in the illusion. Sorry. Right. So that's where you expect it to be here. This is where you expect the peak of this curve to be if there was a full illusion. But it falls in between the two, saying that there is about 50% reset back to the physical location. So Matteo's original data showed 100% loss of the illusion. So 50% is not enough. There could be something else going on there. The real point is, if the saccade itself resets even partially the apparent location of the target, it needs to do that at least 100 milliseconds before the saccade, because there's a dead zone, as some of you know, in saccade programming, where you can no longer change the target. So in other words, this loss of position needs to have happened so earlier than we do think it happened. So the timing of the reset, even though we do get a partial reset, may be too late. Okay, so we looked at that. Saray also looked at spontaneous resets. You may have seen that. This is kind of clever. She has the stimulus moving obliquely, and arranges the internal motion. So it always seems to be a 45-degree angle. And then she tries 3 different delay durations, 1 second to 3 seconds, and 2 different path lengths, but always with the illusion being 45 degrees. And so if there's no reset, so a reset means just spontaneously, it happened to jump back and then start again. If there were none of them, this is the offset you'd expect between the final location of the perceived point and its actual physical location. But if there's some partial resets happening, then you measure less. So that's what you did. Ooh, there's a lot of data here. Look over here in this, the yellow and blue part. This is the real data. The blue bars are the predicted ones, times 1, 2, 3. The expected offset, if there were no resets, would be up here. So everybody is showing some spontaneous resets happening. And in fact, a number of resets goes down as the time goes up, which is a clue that it's probably a function of the time and not the distance. And the same thing happens with the longer path, the 4-degree path, where the perceived offsets are twice as large. And here's her model, random time limit. So the idea is that there's a reset about once every half second. And she can look at, even though the data is only for the endpoints, you can, of course, with the model, look as it builds here. And it's not really building smoothly. That's the average of thousands of trials for the subject, and of course, thousands of trials for the. So in each trial, it kind of goes up and resets, keeps going up. So there's one trial, here's another trial, goes up, resets, goes there. It's all very small. I hope you can see that, and it goes up. So across all those averages, oh, this one had no resets. So across all those averages, this is what you get, and it looks smooth because, well, there's a lot of trials there. So what happened here is it looks like there actually is a spontaneous reset. No flashes needed, no saccades needed, but once every 550 milliseconds. That may be linked to just random distractions or to microsaccades or blinks. We're not sure, but really we know a lot more about that now. Okay, so here's the next point. Where does this happen? Happens in, not in V1. So this is an optical recording by Sandrine Cavanagh and Fredo Chavannes in Marseille. And here on the left is without any internal motion. This is the control case. This is just a Gabor drifting across the monkey's field of view. This is an optical recording from monkey V1 on macaque. And the fovea is up about here. So the actual path is about 4 degrees away from the fovea. And this little black point is the centroid of the kind of blurry, understandably blurry activity that's being picked up as the Gabor passes through the available window that's being picked up in the camera. Over here is the illusory case. Oh, I'm sorry, I did it the wrong way around. Not that it matters. This is the actual illusory case, the black one, and this is the static Gabor moving up, no internal motion. And over here is the trace of all the centroids, the black and the white ones. And I think you'll agree they look pretty similar. And if we just draw a line on them, here's what is the regression of all of those. And here's where the illusion should have been. It should have been taken off. We measured that just for humans, 23 degrees. We don't know about for monkeys, but we think it's about like that. And so they are completely the same and no effect in V1. So we thought this just didn't work. This was a failed experiment. And we only did one monkey. But in fact, now we think about it, it's backed up by the fMRI. So why no downward projections? Well, perhaps because attention is like saccades and is immune to the illusion. And then the downward projection would go to the physical path. So the V1 activity that we got with the flash grab was due to downward projection, but now the downward projections are going to where the stimulus physically is, where the bottom-up activity is. But that means now, okay, V1, well, who cares? It's not there, but now we can find where perception does emerge because attention is not going to be broadcasting perceived locations everywhere. That's our interpretation. And well, optical imaging reflects blood oxidation like fMRI. So let's go do some fMRI. This is Siré and Ching, who did exactly that. First of all, they did an upward, up and down path of the Gabor. Because of the internal motion, either seem to tilt left or tilt right. And they have some ROIs for V1 through MT. And what they find is they cannot really decode leftward versus rightward in V1. They can a little bit in V2 and V3, perhaps because of some local motion cues, we're not sure, but nothing at all in MT. On the other hand, when they take these physically tilted paths that match the subject's judgments of the tilt of these illusory ones and present them, then the decoding is marvelous, up to 90% in V1. So if V1 was actually having these different paths, it would have been easy to find out. Then they went to cross decoding, which is the real key. We trained on the left versus right for the physical paths, and then tried to decode the illusory left versus right, and of course, vice versa. And the successful cross decoding is pretty interesting because it indicates a common representation for the two paths. You only decode them, I mean, they both have the same percept, tilted to the left, tilted to the right. Where does that happen? Well, cross decoding should tell us. And what happened was, my goodness, nothing in visual areas. These are the red circles. No cross decoding, no shared paths in visual. There's little patches there. But the shared decoding happened here in frontal cortex, maybe a bit there, but certainly in the dorsolateral and medial prefrontal cortex. Well, what does that tell us? Well, we could imagine that conscious perception location is really computed outside the visual cortex. Visual cortex, gets the data, but something else is constructing our model of the perceived world in terms of location, at least we can say. And we can only get that far because attention didn't project to any of the perceived locations in early visual cortex, so we can rule them out. Nothing was happening there. And so attention may be independent of perception, like saccades. Okay, now
we have one more batch of questions, if that's okay with you, Professor.
Sure.
One was right at the beginning of this section from Hiromasa Takamura that says, natural vision mechanisms on eye movements and attention are tightly coupled. So that if the eye movement system matters, is it possible or does it make sense to disassociate attention accounts, or is there another theory? So that was one. And then the other one from Gideon would you like me to repeat?
Yes.
Okay.
Well, eye movements and attention are closely linked, yes. And in this study, we seem to find that eye movements and attention are separate from perception. That's kind of interesting. Okay, yeah.
So that, okay, great. And then the second one was from Gideon Kaplovitz, which is, I think it's meant to say, do you see shifts in the resets with prolonged exposure?
Oh, well, I assume you mean, does the reset happen at the same time? Yes, it does seem random. So if you have long duration drifts, you kind of get resets happening every now and then. If you repeat the trial, they seem to happen at different locations. Yeah.
Okay, fantastic. Thank you.
Okay. Okay, so it hasn't escaped our attention that the studies from Dartmouth and the studies in Berkeley show a lot of differences. Now, I won't go through that here. We can get back to it. But there are some similarities, and the study of Gerrit in 2013 and study of Peter Kohler in 2017 have seen the opposite direction results. And so there's a few things that are quite interesting going on here. And I have a theory about what's going on, and we can get back to that in the end later if we have time. So I think there really is a good reason why the Berkeley results and the Cyril Liu and the Peter Kohler results are different. I think it's due to the properties of the illusions we were looking at. So I can say that more about that later. But let me get through what I wanted to tell you here today about the frame-induced position shifts. Now, many of you had the VSS poster, so you've probably seen all of these, but let's go through them. Okay, so this is what we're talking about. Now, here are two red dots. They're actually physically lined up. And now with the frame away, so you should be on your movie site now and onto this movie in your movie site. I'll wait a little while for everyone to make sure they're caught up because I'm pretty sure this doesn't really play that well on the, on the Zoom. Oops, I can't make it play again. Here, hang on. It doesn't want to play again. Oh well. There we go, down here. Okay, so remember the two red dots are lined up, And you can see that here. And I assume by now you're all caught up in the movies. And when the frame comes on, there's this extremely large offset. Okay. Now, induced motion has a very long history. So Johansson, 1950s, did this lovely study of the kind of bicycle wheel, the light that seemed to be doing looping motion, but when you put the center in it, it came back. And then, of course, you could see, I mean, the circular motion. So there's some kind of frame of reference for to organize the motion. And then Duncker and Wallach made a lot about induced motion. And I think they got it from the moving moon that slides behind the clouds. But here's his static target version. And in his experiments, the frame speed is extremely low, sometimes just around threshold of motion to get his effects. But we're going to do something much higher. So here, I think you'll see nothing at all. The red dot should appear not to be moving. I mean, I don't see it moving. I don't think anyone sees it moving. In fact, in the papers that do study induced motion induction, the speed of motion is usually pretty slow. So here's one from Ikuya and Shin, where there's a background motion. And you might see that little circle moving. Probably not, but done properly, you would. Their speed that they used, maximum speed, was about 1.3 degrees per second. So relatively slow. Nakayama and Tyler, both here as well, did a different one where the outer bars move up and down or in and out, and the two static inner ones appear to breathe the opposite way, compress and expand. And this may not capture their effect, but there again, the speed limit was very small. The speeds they used was very slow, and their maximum speed was 1 degree per second. We're going well beyond that now, as did Wallach in 1959, when he took an up and down, he took Duncker's effect and made the target move instead. And now when the frame came on, it was an enormous effect. Now this red dot is always moving vertically. Also, Gogol, if you know the literature, did a number of excellent studies, one of them involving attention, which I won't show you here. I just showed you his diagram. He makes red and blue go opposite directions. They go back and forth this way, and then there's a vertical dot moving up and down, and asks you to pay attention to the red or to the blue, and when you do, you see different directions of motion. So you can show the induced motion attentional effects. Now, what we added to this was quite simple. Instead of looking at moving targets, we look at just flash targets. And what we can do to kind of compare their strength is we can try and null them. So here in your movies, if you're following along, the frame moving back and forth makes those two flashes appear to look more or less vertical. Of course, it's probably different for each of you and for different sizes of stimuli. I think one thing interesting is the effect doesn't really matter too much where you're looking. You can be looking at it, you can be looking in the periphery, still about the same. So it took about a 42-degree tilt to null this effect of the frame. But if we go to the continuous motion, the Wallach's effect, it gets nulled with about 20-degree tilt, maybe half as much. And even when it does, you can still see, well, kind of, yeah, it's moving vertically, but it's also shifting left and right. So it's quite, it's a bit of a different effect. Now, when you're doing the two dot flashes, the interesting thing is it's quite global. It's not like the flash grab and the other effects, which are quite specific, quite local, or more local. This seems to have the same effect. Very few of the dots are showing up for me here. I hope on your movie they all show up. The effect of the offset is about the same no matter what the size of the square. In fact, you can look at how much of a frame is a frame by adding a whole bunch of dots. So these two dots flashing red and green are superimposed, but as the background moves back and forth, they seem to be separated. Again, doesn't really matter too much where you look. And now I'm decreasing the number of dots on each cycle until there's very few dots. Seems to still work with 4. Okay, at 3, 2, maybe, yeah. 1, I'd say no. So what's a frame? Well, at least 2 dots makes a frame. And of course, you could ask that about squares and so on. Here's another question: does it really still work outside the frame? So look at these two bars, red and blue. They're actually superimposed. And when they get outside the frame, well, it depends on, I see some effects still outside the frame. Not as large as when they're inside the frame. But here I find a different story. You may or may not. So again, inside the frame, there's a large effect. But when the frame moves off in the same direction as the motion, now I find very little effect. A little bit, some still left. So it does seem to matter about being inside the frame to some extent. Now here's what Mark Wexler was working on that I think is really quite fascinating and maybe helps us understand why this effect is here or what it's part of. What Mark has done here is make the rectangle jump in apparent motion. There's no intermediate positions. And I don't get many dots on my image. So this one you really have to get in your accompanying movie versions. And I think if you do see the two dots, you'll see, oh my goodness, these dots seem to be very separated. Some of the frames I'm getting both dots. I hope in your movie version you get both clearly. Every time I do get the two dots, they are very well separated. They're separated almost by as much or as much as the frame travel itself. And notice that this is like an infinite speed, a single jump of the full distance. So this says this isn't really speed limited. And it says it's perhaps quite related to visual constancy and the correction of location after saccade. So every time you move your eyes, of course, the entire world is your frame and it shifts with your eye movements. And what this is telling us is that if that's the case with a really big frame, all of the position judgments should remain unaffected. Things are where they are in the world, despite your eye movement, because of however this frame movement, this frame effect works. So that's why we are really hoping to follow this up. Now here's a little bit more about how many dots make a frame. Here's two dots that are jumping back and forth. They are vertically aligned. Some of you might want to stick your hand in front to make sure they are really aligned. But the huge frame effect only happens when the dots move in tandem. In other words, when they are kind of like a frame moving back and forth. When they move out of phase, 90 degrees even, or 180 degrees out of phase, the effect is lost. Well, it's not totally lost. There's a residual offset, one that we in fact measured in 2013, not knowing the huge difference between in-phase and out-of-phase dots. We think that residual effect is what the motion-induced position shift is. And we're not sure about that. But it may be one way to isolate the motion-induced shift from the frame shift. Here's something that Stuart added that's quite nice, asking if you have two frames, which one rules? Well, I think you can judge as it is. The two red dots are always in the same location, but they may seem vertically offset when there's only that vertical motion, but when you put the two of them together, I only see horizontal offset. So the inner frame rules. And finally, here's just for fun, 3 dots. There's a rotating background like this. There's 3 dots. Those 3 dots are totally superimposed. And for most of us, some of us at least, the 3 dots look to be quite offset. So we can do some interesting further tests. Okay, so let me stop because we're over. Moving frame shift the position of flash tests by a whole bunch. This is a very large effect. I didn't take the time to point out, but it is large enough to move the apparent position of a flash from one hemifield to another. So if in those squares with the 2 flashes, I'd asked you to fixate 3/4 of the way between the left and right end of the frame, the one flash would have been moved from the left hemifield to the left hemisphere to the right hemisphere, even though it's physically never presented there. So there's really a lot of opportunities here to use this to study where perception emerges. And we hope to track down why or how this relates to visual constancy processes. Now, we don't really know. I gave a little hint about the 2 dots moving in phase or out of phase. We don't really know how to differentiate phase effects from motion effects because, of course, they both have some frames going on and they both have some motion going on. So and maybe they aren't different. Maybe they are. And so hopefully at some point we'll be able to isolate one from the other. And hopefully at some point we'll know how frames are, what are the algorithms, you know, where does this happen and how does this work? I mean, it's one thing to say, oh, well, you get this into a frame specific set of coordinates. Of course, that just repeats the result. It's not a mechanism. Someday we might have a mechanism there. Overall, we find some large illusory offsets, gives an opportunity for tracking development of perception. The double drift was a really cool one because it didn't seem to have any feedback to illusory locations. It just seemed to have feedback to the bottom-up location like saccades do. So that's a bit of a conjecture there, but we think that will hold up. Well, we're going to find out. And what we did find there was that some representation of position, some representation of the perceived locations seems to emerge very late outside the visual system. Now, interestingly, the frame-induced position shift has an even larger effect. So that opens up all sorts of new opportunities for us to study this. And we don't really know how or where it happens. Or whether there's feedback of illusory location to early visual cortex. Although Josh Solomon just sent me a paper that maybe suggests there might be. Anyways, that's it. Thank you.
All right, fantastic. We definitely had a fair bit of questions in this last section.
Okay, I think if I stop sharing the screen, I can actually see them now in the chat window. So come back, chat window. Oh, there they are, lots of stuff. Okay, so you had Shin, Christopher, Hiromasa, Arash, Ken, yeah, and then Suzanne, thank you. Well, thank you, Suzanne. Okay, so those are the questions we have. So I can start answering those. We already went through Gideon's about the resets with prolonged exposure. There are many and they're kind of random. From Shin, the whole thing seems to be consistent with 2 points. I'm reading his question. Timing of decision decoding, EMs, eye movements are in general shorter. Yes, there's a speed. And when longer, more room for postdiction. Ooh, postdiction outside the visual cortices. I think I agree with you, and certainly we don't know yet about the frame and effect, whether the time constant is so long as it is for the double drift. But Matteo Lisi's feeling was exactly what you're saying here, Shin, that the eye movements have to be fast. They don't have time to accumulate a large history. Whereas the perception has a much larger, much longer integration period. I hope that answers your question. From Christopher, Nakayama and Tyler in that lovely 1978 paper measured the full frequency range. And yes, there was some interesting, it tailed off very early, like I can't remember, maybe 4 or 5 hertz. It doesn't really go very far up. I think that's an interesting point. Same thing for the frame that you saw. I mean, moving the frames back and forth, exactly same thing. And Mark Wexler measured that and said that about 4 or 5 hertz it fails, and we find that as well. So that's completely true. So there must be some, of course, deep and important links between the induced motion and this frame effect on position. I don't think they're totally exactly the same thing, but they're pretty close. From Hiromasa, induced motion is stronger. This does not have a hard edge. Gabor, I guess you move the flash. We may eventually have a much weaker position cue. Wondering if the presence of position cue matters. Well, what you said is true for the double drift. The blurred edge is very important for that double drift pattern, which is moving up, but it's perceived this way. That only happens best if the Gabor is a Gabor and has a smooth edge. But for the frame effects, we don't find that at all. All the stimuli we showed you are sharp-edged, flashed with no attempt to blur in space or time. So I think your point is true for the double drift, but I don't think it's true for the frame effect. And for Arash, hi Arash, we should be able to intercept moving objects accurately or we will die. That's true. This is really a do or die, life and death area of research, right? Luckily, our motor system seems to be more or less immune to the double drift illusion, yes? Why do you think our visual perception is subject? Yes, okay, well that's a question about the double drift again. So it's where the perception and the saccade differ. We don't know that about the frame-induced effect yet. But certainly for the double drift, it is true. And our thinking there is very loose, that in fact, it's just a very rare stimulus, and that moving things with motion inside them are kind of limited to cuttlefish. You've probably seen lovely examples of cuttlefish videos, and cone jellies, and maybe soccer balls, but they move too fast and tennis and baseball, they're probably moving too fast for you to pick up the internal rotation. But we do have kind of an anecdotal point there, and that is that some of the subjects, after months of testing, have less and less effect. So as you say, we're trying to learn the correspondences of location and motion for objects, and this is just an object, the double drift with the internal motion. It's an object we've rarely encountered and haven't been able to calibrate. Perhaps with long exposure, months, we might make the illusion go away. That doesn't sound like much fun, but that's the thought. How does this relate? Ken asks, how does this relate to Johansson's vector analysis? Well, yes. Well, his vector analysis was like to bring all the motion vectors in relation to the centroid of a moving frame, and exactly that. But now we're dealing with position, so the position within a frame. And I think David Whitney mentioned that that's related to the Roloff's effect in a way. So there's almost 100 years of work on frame effects, so there's lots of literature to catch up on. I think well, I don't know. Johansson's vector analysis is about understanding objects as they move. So a person waving on a train, you see them waving, you don't see the sine wave of the trace through visual space. And that's quite useful to understand the object, so object-specific coordinates. It may be different from the frame, flash, and the effects, the advantage of that for visual constancy. So I don't know, they're certainly strongly related. I don't know if the displacement ones have some extra importance. Oh, some more questions from Jerry. I'm not sure what that says. Can someone translate? Shin?
I'm not Chinese, but I think she just said bye. Maybe not.
Oh, bye. Okay, bye. Bye, Jerry. Okay, Jeff, double drift is an example of Q conflict being first and second order motion. Yes, have you studied whether these different types of motion do different size effects in the phenomena that you look at? If you're asking, Jeff, about the frame effects, we've not tried anything yet with first and second order motion frames or targets. Some of the induced motion studies, I believe, did the second order motion. So I can't really tell you anything there, but certainly something to be studied. From Gideon, the red-blue flash version of the FIPS works so strongly under direct fixation. Awesome, yes. Well, the red-blue flash is one of the few ones where the two flashes were at the same location, whereas the other ones, the two flashes were separated. I don't get that much of a difference between peripheral and central fixation for them, but there could be something going on there. I don't, as long as I'm sort of not fixating one of the flashes, I don't find much difference between being inside the box and outside the box. But certainly something to be studied. Miriam, frame effect. What is a frame? Yes, of course, like what's an object? Okay, related to relative positions, elements in the scene, if complete dark and only one other object in the field. Yes, so that's what I was trying to get at with the set of dots. And now, as you saw with the two dots, they didn't surround the object, but I think there was still a pretty strong effect. So I don't think they have to surround, but it seems pretty lame to say, well, one dot's not enough, but two dots are fine. Perhaps if instead of a dot, we'd use a line, maybe one line would be okay. So I don't really know at what point that context breaks down as a frame. Certainly lots to ask there. Hang on, from Gideon. That is what I meant by prolonged exposure. So you're getting at the anecdote of people with lots and lots of exposure, yes, they get more resets and less of an effect. You're right there. So there is some kind of learning going on. Jerry, mistypes, sorry, okay. And Garit, what about the difference between, oh, did you want to go back? I don't know. Perhaps those who need to run on can leave, unless you have some other questions, and then I can go back to the Berkeley versus Dartmouth imaging differences, and because I think there's an interesting point there. So do you want to take a little pause while I go back? Because I'll have to reload the screen sharing here. Okay, David, why don't you take over and use some voice while I'm backing up, and then I'll share screen.
Oh, you want me to take over?
Yeah, just say something to fill the void while I'm backing up in the slides.
Actually, I was thinking, Ken, do you want to give a postscript or an afterward? Oh, he wants to clap. Where's Bill? Bill, you want to count for us?
Bill, you need to make sure you unmute and explain what we're doing first.
This might be an illusion.
Hi, Bill.
To celebrate with one clap. I don't know where this happened, but I'll have to on three. 1, 2, 3.
Whoa, that was large. I see the waveform behind Jerry on his background too, yes. Okay, Mark, do you want to step in? No? Okay. Okay, so I'm ready with the slide about Dartmouth versus Berkeley. Is everybody okay with that?
Fantastic.
Gotta go, Dennis. Bye, Dennis, it was nice to see you. Romy, okay, bye. Okay, we're up to date here. Okay, here it is. Okay, now I'm going to share screen again. And we're back to this slide, Dartmouth, Berkeley differences. So this is just a thought I had, because I noticed, it's not too hard to notice, that a lot of the results are not, some correspond and some don't. So first of all, here's the first point. So I'm not going to animate these anyway. These are just, the first point is up here. Early visual cortex represents retinal, not perceptual coordinates. That's what Saray and everyone at Dartmouth said this year. That's also what Jason Fisher and David said in 2011. Okay, so remember that we're thinking that perceived location should feed back to V1. So how is it that Fisher et al. Didn't find top-down values in V1 in 2011 and made pretty much the same claim that we did, that visual cortex is bottom up and perceptual coordinate are later. So we'll get back to that in a moment. But first, here's Garrett in 2013. This is his graph here, this little one on the left, and they found that MT, that's this bar, was stronger than V1, and there's really not much in V2 and V3. So things got bigger as you went higher up. Whereas Peter Kohler and Peter C. and me found the reverse. The V1 was the strongest, and then it got less. Okay, so why is that different? And we'll get into the stimuli in a moment to see. So, so Peter Kohler says visual cortex reflects perceptual coordinates because of attention, not because of early shift. Well, certainly Garrett and Jason were not finding any early shifts or early effects matching perception. But Peter Kohler was, and claimed it's because of attention, not because of shifts in neural activity. For the double drift, attention doesn't project to the expected perceived locations. That's Saray's claim, consistent with Kohler. So Kohler says, oh, we got something in V1 because of attention. Saray says, oh, we got nothing in V1 because attention doesn't go to the perceived location for this particular illusion. It's special that way. It goes to the physical location. Fisher and Mouse, on the other hand, say, oh, well, we didn't get any effects of attention in V1 because we had a really good distracting attention task. And so attention really wouldn't have gone to those targets. I'm not too sure about that. So here are the 4 different stimuli. So this is Fisher and Spotswood and Whitney. This is Mouse and somebody in Whitney. This is Kohler and C and Cavanagh, and this is Liu et al. Okay, this is the double drift. This is the flash grab. This is the flash drag. These little bars here are dragged in and out from the fovea. And these are the Devoloi things that drift towards or away from the fovea. Okay, so my, my point here is, my thought here is, these experiments had quite small perceptual shifts. Their effects were reliable enough that they could be picked up cleanly with the techniques to use. So there's no question about identifying the shifts in the cortical areas where they were found and being able to reject any shifts in the cortical areas where they weren't found. Nevertheless, they were quite small. In fact, I went back and calculated what they were. And for Fisher, well, it's kind of an error thing, but the effect, the shift, the main shift for the effects were about 0.3 degrees at 9 degrees eccentricity. For Garrett mouse, it was 0.5 degrees, sorry, 0.3 and 0.15 degrees at 8 degrees eccentricity. So both of them less than half a degree. For Peter Kohler, this one, oops, Peter Kohler, this one, whoops, I keep pushing the wrong thing. Okay, I begin to do this very carefully. Okay, here we are. This guy, Kohler, this shift was 1.7 degrees at 8 degrees eccentricity. And for Liu, the shift was 5 degrees at 8 degrees eccentricity. So this endpoint is 5 degrees visual angle away from the physical. So the point is that attention has very low resolution, and its projections back to V1 are going to not be able to pick up these shifts of like 0.3 and 0.15 at 8 degrees eccentricity in these experiments. And that explains why they don't get the shifts until later. Because attention was doing its best to project back the locations, the perceived locations, but attention is a very fuzzy operator. On the other hand, these ones have shifts of almost 2 and almost 5 degrees, and also at 8 degrees eccentricity. So certainly enough for attention to project back to V1. So that's my thinking. I don't have any way to prove that, but I think that all these studies are saying the same thing, but because of the size of the effects used in the Dartmouth studies, attention had the chance to project back some very easily detected offsets in area V1, and to not send them back here when the offset was 5 degrees, because in fact the attention was feeding back to the physical location, is our conjecture, not the perceived location. So that's my take on the Dartmouth-Berkeley differences. I hope that is okay with you, Gerrit. Okay, that's it. We got to go. Everybody's go. Bye, says Christopher. Okay. David, anything else?
Thank you, Patrick. That was wonderful. Anybody else want to ask any more questions? Okay, that's it. Hey, Patrick, thank you again for that wonderful talk.
That was fun.
Thank you so much.
Okay, this is this is my first electronic talk. I think it's fun to do. I hope that maybe give me some feedback. I hope did the movies work on the extra website?
Yes.
The movies on the other website were awesome.
Yeah, that because on the Zoom they're just not working at all. Okay, good.
The website was wonderful. Very good way to handle that.
Okay. Okay, well, it's now 11:20 in Strasbourg, so and 10:20 in Oxford. So those of you in Europe, and of course the part that used to be Europe but is now separate England, you should all get off to bed. And those of you in Japan, some of you waking up, time for some coffee. It was good to see you all. Bye-bye.
Thank you.
Thank you once again.